Hi, my name is Jerry Lynch. I'm the Donald Malloy Department Chair of Civil and Environmental Engineering, and I'd like to welcome you to the Universities of Michigan's Building the Future Distinguished Lecture Series. The beginning point of this lecture series was an effort that we undertook as a department many years ago, looking at developing a strategic vision for the profession of civil and environmental engineering. In 2019, we published our strategic vision, which included 5 strategic directions, including enhancing human habitat experiences, shaping resource flows, automating infrastructure services, smart infrastructure financing, and adaptation. This is a very exciting vision for both our department and we hope for the profession. The vision also reaffirms our value proposition to our communities as we work in service to build a better and a more resilient society. This lecture series is all about highlighting the strategic plan. More importantly, it's about building a broader community of stakeholders that includes industry professionals, researchers, educators, and students to explore each of the strategic directions that the plan enumerates. Through presentations from leading experts and panel discussions that bring new insights, this series explores a range of perspectives that can help inform how we move forward in each of these strategic visions. Today's lecture will be focusing on one of those directions, specifically the direction of adaptation, looking at how our society become more resilient to some of the external stressors that we're seeing, such as climate change. Now, before introducing our speaker and our coordinator of the lecture, I want to first thank a number of important individuals that made this event possible. First, I'd like to thank the co-sponsors of the event, specifically the American Society of Civil Engineers Engineering Mechanics Institute, and as part of EMI, specifically the Objective Resilience Committee. We'd like to also acknowledge the sponsorship of the Great Lakes chapter of the Earthquake Engineering Research Institute, also known as EERI. I'd like to also thank the Strategic Implementation Committee that planned this event. This committee's been led by Professor Sang-Yoon Lee, and we're very much indebted to Professor Sharif Al-Tuel, who's also been leading the organization of this event and has also agreed to serve as a panel moderator. Before transitioning to Sharif, I'd like to highlight some of the accessibility options that we've made available for participants. We wanted to make our event accessible. So this webinar will have a live automated caption as well as a transcript that will be made available after the event. In order to elect these options, please click live transcript on the control bar at the bottom of your screen where you can show or hide the subtitles or view the full transcript. So without much further ado, I'm going to turn it over to my colleague, Professor Sharif Al-Tuel. Sharif?
Thank you, Jerry. I would like to welcome everyone participating in today's event. Today's distinguished lecture emphasizes the strategic theme of adaptation. To give an overview of this theme, I would like to play a 2-minute video. Adaptation is a necessary thing for survival. We're dealing with many things that are affecting our life. Climate change is essentially raising sea levels, and that's going to affect coastal communities. It will cause more severe storms, more severe hurricanes, and tornadoes that are becoming increasingly frequent and increasingly destructive. We are looking at how extreme events like hurricanes and earthquakes affect communities, and how can these communities recover quickly from these different types of events. My colleague Evgeny Filipov, he's looking at how origami can help us design structures that change shape, that respond to various types of hazards as they occur. My colleague Valery Ivanov, he's looking in the Amazon at how trees interact together and how they grow within that environment. My work is focused a lot on earthquake engineering. If we do not build our structures to be resistant to earthquakes, we are going to get structures that would fail in a catastrophic manner. We will always be adapting to new stressors that will appear on the horizon. We just don't know what they are yet. Through human ingenuity, we will always be able to adapt to whatever situation exists. All right. With this short video, I would like to also let you know that during the lecture and the panel discussion, I would like to invite you to send in your questions through the question and answer function. We'll try to get in as many of your questions as time allows. So with this, I would like to introduce our very special speaker and panelists. We're very fortunate to have Professor Jack Baker, who will speak to us on engineering disaster resilient systems in an uncertain future. The presentation by Jack will be followed by a panel discussion with two distinguished panelists, Chris Poland and myself. And I shouldn't call myself distinguished as I'm presenting this. Professor Baker is a professor of civil environmental engineering at Stanford University, and Dr. Chris Poland is a consulting engineer at Chris D. Poland Consulting Engineering, and he's a member of the National Academy of Engineering. And I am the Nauman Collegiate Professor of Civil Environmental Engineering at the University of Michigan. So without further ado, this brings us to the distinguished lecture for today's, the main event for today. And I would like to invite our speaker, Professor Baker, to get started on this. So Jack, the floor is yours.
All right, good afternoon. Thank you, everybody. I'm really honored to be invited and pleased to be here. I'm impressed by your departmental vision and I'm looking forward to the chance to share a few thoughts on these topics, primarily in my field of disaster risk assessment. So let me pull up some slides to talk about here. Okay, so I'd like to talk to you about engineering disaster resilient systems, thinking about the resilience aspect of this as it ties to adaptation, and also thinking about the uncertain future we face and what role that plays in this concept of adaptation. And I'd like to start with just for a few minutes thinking about kind of some personal observations and experiences that kind of motivate my thinking about this. So the first one comes from Christchurch, New Zealand. So this is a well-known photo from 2011. There was a quite destructive earthquake that occurred right underneath the central business district of Christchurch, New Zealand. And this is a photo of the dust thrown up by that earthquake as buildings were damaged and collapsed. And incredible tragedy. 185 lives were lost. There was quite a bit of damage to unreinforced masonry and other vulnerable buildings, the vulnerabilities we understand as an engineering profession. But I had the chance to go there in 2015 for a year on a sabbatical, and was kindly hosted by University of Canterbury. And so this is about 5 years after the earthquake. And 5 years afterwards, the central business district looked a lot like this. So there was some buildings remaining, but a tremendous number of vacant lots as buildings had been torn down and demolished. And many of these buildings that are sitting here were sitting vacant as planning was underway of what to do. So many of the buildings in this area were torn down for a variety of economic reasons. The reconstruction was put on hold for some time as the city thought about kind of a master plan for rebuilding. There was a safety cordon placed around this entire region for some areas were in a cordon for up to 2 years, as it was deemed kind of unsafe to be, for have citizens of the community in that area. And there were safe buildings inside that cordon that were inaccessible for long periods of time as the neighboring buildings were being dealt with and the damaged infrastructure was being dealt with. And so the factors influencing the recovery here went far beyond just the safety issues associated with the most vulnerable buildings in the area. It was a much more kind of complex process. And this has been observed in many situations, but my chance to observe some of these features up close really drove my thinking about these problems. Another really compelling issue that was faced there is what occurred in what's called the red zone. So this is a photo outside of the central business district, kind of between the city and the coast. And this area used to be kind of a fully developed residential community. And there was very severe liquefaction in this area. It was quite low lying. You can see the Pacific Ocean in the background of the photo. The water table was very high and really severe liquefaction, maybe as severe as we've ever seen during an earthquake. So that caused tremendous damage to a lot of buildings. The buried infrastructure was really severely damaged, and there was a lot of subsidence in the area. So some areas were actually below sea level after the subsidence occurred. And so as there was kind of a repeated liquefaction in a series of earthquakes, it was just deemed that this area was not inhabitable anymore safely. The flood risk was too high, the liquefaction problems were too severe, and ultimately 10,000 people were relocated out of this area, and with tremendous disruption. And I think looking at that, I think it's a harbinger of what we're going to see with sea level rise and managed retreat. Is a very painful process. And very disruptive. And interestingly, when that subdivision was built, none of this was foreseen. Right, there was no consideration of severe flood risk in the future. The liquefaction problem was not on people's radar. It wasn't deemed a very high seismic risk area. And so a built environment was built under a set of assumptions that no longer held, and we faced the need for adaptation. And so again, I think this is illustrative of the type of challenges we're going to face moving forward. A second situation that drives my thinking about adaptation comes from closer to my home, where I am now. This is just a little ways north of me in San Francisco, and the seawall around San Francisco is an interesting problem. So this is the skyline of the city, and then to the west, or to the kind of left and bottom of this photo, along the waterfront there in San Francisco Bay, there's a seawall that's been built up. So like many cities on waterfront, there was artificial fill kind of pushed out into the bay to expand the land along the waterfront. And so we have this kind of low-lying area protected by the seawall that was built more than 100 years ago. And there's a couple challenges that this area faces now. So the first is that it's extremely low-lying. This is a photo taken from down on that seawall at an extreme high tide, a king tide. And on these high tide events, the water from the bay can overtop the seawall. And of course, this problem is only going to get worse with each passing year. And so we have a flood risk problem now with a tremendous amount of assets kind of right behind the seawall. Additionally, because this land is artificial fill, it's very susceptible to lateral spreading and earthquakes. And indeed, it's experienced lateral spreading. So this is a famous photo from the 1906 San Francisco earthquake. And this is the seawall, that same seawall that's in the photo, where lateral spreading of that seawall out into the bay caused the roadway at the time to slide out and be severely damaged like this. So that same problem exists today. It's the same artificial fill, except now there's billions of dollars of buried infrastructure in that waterfront, and there's billions of dollars of buildings sitting right behind it. So the city faces this challenge of this present risk of earthquake damage to the seawall, and this growing risk over time of floods due to sea level rise. And ultimately, is in the planning process of what's going to be probably a $5 billion project to retrofit and raise this seawall and improve its safety. And we're designing for a future that doesn't look like the past, right? And again, a harbinger of what we're going to face as a profession. So with that as kind of some background and specific examples that are illustrative of situations we face around the world and will increasingly face, I want to talk today about two challenges related to adaptation. So one is, how do we design for resilience, right? Our profession has a long and distinguished record of designing for safety and keeping occupants of our buildings safe in extreme events and normal operations. And I think we should be quite proud of that. But increasingly that bar is moving, and we need to think about other performance objectives. And then the second is, how do we design for a future that doesn't look like the past, right? That really throws some of the paradigms we've used in our profession into question, and we need to develop some new tools to address that. So I'd like to talk briefly about both of those topics. So first, let's talk about resilience. And I think if we want to think about where to go, we should think about where we are right now. And so I like to go to the ASCE 716 standard. So this is an important standard that drives a lot of our design and analysis procedures for buildings and other elements of the built environment. And if we look in at the performance goals in there and look at the commentary, I took some of the text out, and it's on the slide here to the left. And so it says these standards and these performance objectives were intended to provide protection against structural failure, right? It's structural failure, safety of occupants that is primary in our goals as civil and structural engineers. And then the commentary goes on to say, we would like to provide economic protection. We'd like to improve the probability that critical facilities will be functional after small and moderate events. But there is no documentation of the reliability intended with respect to these goals. So they're aspirations, but they're not goals that have been calibrated or addressed explicitly in our design codes right now. And I think that objective is changing, and we're shifting towards a more explicit targeting of reliability and performance. And I think that's going to really continue to be an important part of our profession. To give a couple examples of how that's happening. So one, I think, really pioneering effort, and one that influenced me personally, was from the San Francisco Planning and Urban Research Association about a decade ago. And I'll note that this was led by Chris Poland, our panelist, joining in a few minutes. I had this slide in the presentation even before I knew that Chris was the panelist. So I'm very pleased with your wisdom in selecting him to come here today as well. But this was really a critical effort in getting together stakeholders in the city to look at a variety of functions in society, from critical infrastructure systems to businesses to residences and all of the activities that take place in the community. And to say after an earthquake and more generally after a disaster, when do we need these services to be back at various levels of functionality and setting kind of target resilience objectives. And then there was an effort to assess, where is our community at currently? And when there are gaps between what we want in terms of resilience and what we think we have right now, we need to look at policies and actions to close those gaps. And so this was a really critical framing of this problem to say, how are we going to set objectives and how are we going to go about trying to meet these resilience objectives? So in the decade plus since this report came out, lots has happened. Here's a couple reports that I think are quite interesting. The NIST report on the left is in 2016, kind of expanded on and refined the vision from SPUR for community resilience planning. Just earlier this year, the report on the right came out from FEMA and NIST as part of the NEHRT program, talking about what are options we have for thinking about this functional recovery in the earthquake world, and how are we going to get there in terms of building code changes and other types of options we have at our other levers we have to pull. And I could give a full talk, and others might be better than me at giving a full talk just about all this resilience activity that's going on. I think it's really exciting, and there's going to be a lot happening in the coming years as well. But I'm going to talk a little bit about kind of how some of our research tries to contribute to this or thinks about these concepts and where we might be going as a profession. So to me, and with my own work, I think there's two critical tools that help us solve these problems of getting to more resilient communities. So one is thinking about regional recovery. So here is kind of a paradigm shift from thinking about buildings as islands. When we think about the safety of a building, we can generally treat that building as a self-contained unit. When we think about recovery, we have to look beyond the building envelope to the infrastructure services that are being provided to that building, to the broader economic and social context that building sits in, and what services a building or a built asset is intended to provide to a community. And so we have to put that all together in a regional simulation and think about the recovery of those services over time after a disaster. The second tool that I think is really compelling here are performance-based engineering standards. So this is thinking about kind of specific performance targets and objectives that we're trying to achieve with our engineered systems, and then thinking about kind of assessing that performance and then designing systems to achieve those performance levels. I think that's really critical as we think about a broader set of performance objectives. And it's increasingly feasible to use these tools at kind of the city scale, the regional scale. So I'm going to talk about a couple of details of this and a couple of examples. So when we think about these regional recovery simulations and performance-based assessments, we kind of go through the following assessment procedure. So we think about a disaster or disruptive scenario. For my group, it's oftentimes earthquakes, but lots of this thinking applies in other contexts. So if we have an earthquake, that earthquake produces ground shaking throughout a region. And it's the ground shaking that oftentimes drives a lot of the damage to the built environment. So we think about kind of simulating the ground motion throughout a region, and it's going to vary throughout the region that we're interested in. Then for each asset that's in that region, buildings or infrastructure components or other types of built assets, we're going to think about the damage to those assets due to the ground shaking or other mechanisms. And then we're going to use these performance-based standards to try to think about the consequences in terms of not just safety, but also costs to repair, and then importantly, kind of time to recover and time to restore functionality. Then we can take those metrics for the individual buildings, bring it to the regional level, and look at what does that mean in terms of the economic sector impacts and recovery. So how are we losing services, and ultimately kind of looking at individual households. So how does the loss of housing impact households? How does the economic disruption impact households in terms of lost income or employment, and how does all this come back online over time, and what does that mean in terms of the well-being of those households? And so we can put this all together in a modeling framework and try to understand and then adapt our systems for better performance. So kind of taking the middle slice of that figure, I want to talk for just a minute about performance-based engineering assessment. And here we lean very heavily on FEMA P58. This is a procedure first published now almost a decade ago, kind of building on a decade or so of prior work. And it's increasingly being used in the practice of earthquake engineering on the West Coast of the US especially, but internationally. And the general idea is we start with kind of a ground shaking amplitude, and then we do kind of the classic structural engineering work that we're very good at, thinking about structural responses for a building that we're studying. And this is, drifts, displacements, accelerations throughout the building. But then we continue beyond that structural response to look at damage to individual components. So this is both structural components, the core of the structure that we're responsible for as engineers, as well as non-structural components, the mechanical equipment, the finishes, and other components of the building that could be damaged. And then we kind of assess that full set of damage, and then we go on to our performance metrics, and we say, how much is it going to cost to repair all of that damage? How long is it going to take to reoccupy the building as we're working through the repair process? What is the recovery process going to look like? And so that's kind of the general framing of this problem. And as I said, this is used increasingly for individual buildings. So new buildings are being designed using these types of procedures and try to kind of iterate the design in order to limit damage to components and prevent kind of closures and downtime. And this is kind of a detailed study of individual buildings taking hours of time. But increasingly, we're also using this at the city scale. So if this kind of work on the slide here is the work for an individual building in this assessment procedure, rather than kind of building a detailed model building by building of each component, we're taking kind of city level inventory of more basic characteristics and saying for each building in the region, how old is it? How big is it? What's its occupancy type? And then we're using that to infer the characteristics of the building, right? If we know its age, we can estimate the design standards that were used to design the building. If we know its occupancy type, we can estimate the contents that are inside the building and the components that could be damaged. And so we can automate that. And then we can run, high performance computing makes it easy to run these simulations for thousands of buildings now. And we can get to these kind of outputs in terms of repair costs and recovery time on a building by building scale that we can feed into regional recovery models. And an example of that type of work, this is done by Ann Holsey, a former student at Stanford, with my colleague Greg Dearline. And we were looking at San Francisco. So San Francisco was worried about this cordon issue that I mentioned from my Christchurch motivation, where safety issues might cause us to close down access to parts of a city. And there's a number of tall buildings in San Francisco that are older, pre-Northridge steel moment frame buildings. And we know they're vulnerable to particular types of damage. And after an earthquake, the city is worried that damage to those tall buildings might cause these safety cordons that would cause otherwise safe buildings in the downtown region to be inaccessible for some period of time. And so what Ann did is built a model of the Central Business District of San Francisco, ran this FEMA P58 assessment for the entire downtown region through the procedure I just talked about, and then went to this regional recovery simulation phase. And so what she did is she took the kind of all the buildings in the area, assessed their kind of damage and downtime, paying special attention to those tall buildings and even refining the modeling on the tall buildings. And if those tall buildings had damage that were deemed to be a safety risk, we would trigger in the simulation a cordon where the surrounding buildings would have restricted access. And so those buildings wouldn't be accessible for some period of time, even if they were undamaged. Then we can take the kind of full downtown as a whole and look at various points in time after the earthquake, how many buildings are in the process of being repaired and might not be accessible? How many buildings are waiting the commencement of repairs? We call this impeding factors. How many buildings are inside of a safety cordon and so inaccessible? And we can count up kind of the amount of office space that's available over time and how the recovery happens. And this helps us understand kind of the potential drivers of closure in a future earthquake. And it also helps us measure the benefits or the potential benefits of mitigation actions, right? If we have preparations ahead of time for inspection and planning around those cordons, can we speed up this recovery process? If we required retrofits of various types on these tall buildings, how much difference would that make in terms of this resilience assessment? And so this ability to kind of interrogate and understand the benefits of adaptation, I think, is really critical in this type of analysis and pretty exciting. A second example of this type of analysis, now I'm looking out to the broader San Francisco Bay Area. So the map on the left is the broader San Francisco Bay Area with a population of about 8 million people. And so this is work by a former student, Maria Markvita, and some colleagues at the World Bank that helped with the economic modeling. We similarly simulated damage to built assets throughout the region, and then looked at what did that mean in terms of economic losses, loss of production by firms, and then what did that mean for households that either kind of lost housing or that lost employment due to the economic disruption. And we looked at their household consumption changes due to this disruption. So this was for a simulation of a earthquake over on the east side of the bay. And I'll run this video through in a couple stops. So this is a kind of stepping through in time. So we have an earthquake occurring, and all of this red is indicating kind of lost consumption, so economic hardship for households. And then, over a period of years, this is coming back as the reconstruction is happening and the economic activity is picking back up again. And then I'll pause here, maybe 3 years afterwards in this simulation. So we're getting to kind of blue colors in the map, indicating some areas have actually, surpassed their prior consumption in this process, but there are still patches of red in the map. Those patches of red are in areas that were very strongly shaken in the scenario. They were right underneath kind of where the earthquake occurred, but those are also areas that had various levels of kind of economic limitations. They tend to be kind of lower income parts of the region or less economically vital parts of the region. And so we can couple in both the kind of economic aspects of the community with the physical aspects of the community. And then again, an important thing that we can do with this type of simulation is we can rerun it, changing different inputs to the model. And so here on the right, this graph is a little hard to kind of walk through quickly, but I'll just say we reran the simulations under a variety of potential better cases. So we thought about a reduced building vulnerability simulation where we had a further retrofit policy on vulnerable multifamily residential buildings throughout the whole region. Some of those policies are already underway in the region. We thought about scenarios where we had increased penetration of property insurance. We thought about scenarios where we had a more generous unemployment insurance to cover households who lost employment due to the disaster. And we could look at, how does that influence the consumption of households through this disaster, either by kind of limiting the initial consequences or by helping families or helping households on their recovery trajectory. And we looked at some counterfactuals where what if things were worse than the status quo. And I think this, again, is really valuable for helping us quantify the benefits of taking action. And an interesting thing is we can compare, using the same units, we can compare the benefits of a physical intervention, a retrofit policy, versus a social intervention around a change in insurance policy where the built environment is not changing. We're just trying to help the recovery process to go more smoothly. And I think for stakeholders and decision makers, that's really powerful to get all of these potential interventions on the same set of units so that they can make kind of comparisons across these policies. So this is a kind of a pilot type of demonstration of that decision making, but I think increasingly we're going to be asked to help support those types of decisions with communities trying to increase their resilience. These simulations I think are exciting as an academic, but they're layered up of many assumptions throughout our models. And to understand what needs to be in those models, to try to validate those models, I think we also need to look at empirical data. And so I want to talk to you briefly about a couple examples of that. So this is an example looking empirically at recovery data. Sabine Los, a student at Stanford, is looking at survey data following a earthquake, very destructive earthquake in Nepal in 2015, and looking at households who suffered building damage and whether they've been able to reconstruct and reoccupy their homes in the 5 years following the earthquake. And so she has this kind of surveyed outcomes for these families, and then she's looking at what are the drivers of recovery or non-recovery. And so some of this, she's got demographic information on households and regions of the country. And then she's also got remote sensing data of various types, and did statistical analysis to try to understand what's predictive. And she found, so the initial shaking intensity was strongly predictive, as we might expect, but also things like the population density around the household. How far is the household from urban regions? How remote is it? How much landslide hazard is nearby? Households on steep hill slopes have different recovery outcomes. And so it points to the kind of the complexity of the recovery process that we need to think about when we're trying to understand recovery and predict recovery. And it also is going to help, hopefully in future disasters, to help aid agencies more effectively direct their aid and not just think about the initial damage, but think about the potential for households to recover and what could be done to kind of speed that recovery or make it more effective. We did similar things in Christchurch, working with Erica Seville, an academic in the area, who had done surveys of businesses in Christchurch and their disruption, looking at the drivers of disruption. And it was not just buildings being damaged, but it was also loss of utility services. Some businesses were located in that safety cordon and were disrupted because of that. Some had no physical damage, but had loss of suppliers. They weren't able to get inputs that they needed for their businesses. And so again, trying to understand those details through empirical study will help us further refine our models and hopefully validate our predictions as well. Okay, so those are some thoughts about designing for resilience. I want to speak briefly for a few minutes about designing for a future that's unlike the past. I think this is another critical part of adaptation. I'll show a couple slides from Jack Hogan, a former student at Stanford who's now at Arup, and has some great insights about flood risk. And so this is a slide he put together thinking about flood risk management. And when we think about these flood protection systems like the San Francisco seawall, the traditional approach has been to identify like a 100-year flood level and then put some amount of freeboard above that, and that's how you pick the height of your flood protection system. If we go to a more probabilistic framing of the problem, we can say, well, more higher seawalls or more aggressive flood protection systems, they're going to cost more upfront, but they're going to reduce the probability of a failure and reduce the losses associated with future failures. And so we can think about an optimization where we optimize the total cost, both the upfront cost of the system, as well as the losses avoided, and we can optimize. When we bring in sea level rise, things get more complicated, right? And so I'd say, commonly today, we think about a scenario-based assessment where we say, what's a sea level rise projection in 50 years or 100 years or something like that. And let's pick that sea level rise and put freeboard on top of it. Or let's just pick 36-inch sea level rise and put some freeboard on top of it. We'll design for that. But that again gets it, misses out on these kind of uncertainties. And so the question is, how can we bring in the kind of uncertainties associated with this analysis and bring in the sea level rise change that we have to consider? And so the way we thought about this for the San Francisco seawall was to first think about a variety of mitigation alternatives. So for the seawall, that meant the height of the seawall. And then for a given mitigation alternative, we want to assess the potential consequences. So first, we're going to think about kind of uncertain greenhouse gas emission scenarios. So we don't know, what the future atmosphere is going to look like and future driving of climate change. So we can think about a range of scenarios with probabilities put to those through some judgment. And for a given emission scenario, we can think about a sea level rise projection over the time frame we're interested in. So that's an uncertain projection. And so we can put a range of heights with probabilities on that. And then for a given sea level rise projection, we can run forward simulations and think about the year by year, what's the probability of overtopping the system due to floods, and what would be the economic consequences of the overtopping or some other consequence metric you're interested in. And then we can think out over a lifetime of the system, what's the net present value of the consequences as well as the cost of building the seawall. And so that's going to change over time as sea level is rising, but we can also discount out future losses as well. And so when we take all of this, we can look at kind of expected costs for a given mitigation alternative and then try to select among those alternatives based on these performance metrics. And so this is a much more complex than our traditional way of thinking about designing for extreme events. But we have these tools. This isn't a revolutionary set of tools, but I think these are the types of tools we're going to have to put together to think about future consequences. Thinking about these future consequences, more recently, Corinne Bowers at Stanford's been looking at atmospheric river flood risk. So these are the types of storms that drive a lot of the losses in California from flooding. And with this kind of icon in the upper right of our performance-based earthquake engineering framing, we've been thinking about similar framing for these atmospheric rivers, where we start with kind of atmospheric forcing. So what's how often do the storms occur and how intense are they? What precipitation do they cause? Then we've got kind of the hydrologic modeling part of it, where we get to inundations throughout the region. And then if we've got kind of exposed assets, we can look at how deep the inundation is at the location of those assets and what that means in terms of losses. And again, the value of this performance-based framing is we can think about the losses with whatever metric we want. And then we can think about an uncertain future in this framing as well. So the atmospheric forcing part of the problem is going to change over time as we get more intense storms or different precipitation patterns. And then the bottom left part, this is our adaptation part. As we think about hardening infrastructure or changing our land use planning, we can think about a future that's evolving where the economic consequences are different or other types of performance consequences are different. And again, we can quantify the benefits of taking action and mitigating. And so I think this type of thinking is going to increasingly be a part of our core toolbox as engineers. Okay, so I'd like to start wrapping up now. A few big picture takeaways. I think that the need for adaptation is driving a lot of transformations in the practice of civil and environmental engineering. The ways we've been thinking about our designs are changing. We need to think about recovery and resilience. We need to think about a changing future, and that has to be a core part of our engineering analysis and design. I think the hopeful part of that problem is that, we are building the tools that can address these challenges. And I think we'll play an important role in society in trying to deal with these challenges. They're very interdisciplinary problems. I don't want to say that only engineers are going to solve these problems. These community recovery processes are much more complicated than that. But I do think we'll play a central role in the story, and we need to be ready to step up to that role, and we need to offer the solutions that only engineers can offer within a broader team of experts. I'm going to slide forward for just a second, and I'm going to put this slide up here. These are some of the references to the work I mentioned. I think since this is recorded, if you're really interested, you could go back to the recording and look at that, but I won't leave it up for too long. I will close by just noting at the bottom left here a couple URLs where you can see some more detail about those documents I just flashed and other research that we're doing. And then at the bottom right, I want to acknowledge the many collaborators and supporters that made this work possible. Clearly, it was a great team of students and many collaborators that provided data and expertise and support for this work. So with that, I will close. Thank you again very much for your time this afternoon. I'm really pleased to be here, and I'm looking forward to the panel discussion and Q&A to follow. Thank you.
Great. Thank you very much, Jack, for an intriguing talk and certainly very pertinent to what's happening in today's world. So the questions should please be directed to the Q&A part. I see already there are 4 questions. With the panel discussion, the 3 panelists have decided that there will be no ties. So as you can see, there's no tie. We also decided that this would be a spontaneous discussion where you can, when we get a question, we will just kind of pass it back and forth. So basically there are no rules, and we can comment on a comment as well. All right. So we also remember we had questions that came in through the registration site. So I'm going to start with one of those questions. And the question there was, how can we incorporate a recognition of the power of social infrastructure into our work on the built environment? And before we go any further, I just want to define social infrastructure. It is a subset of the physical or built infrastructure that deals with society, mainly schools, congregation spaces, things like that. That's from our perspective as engineers. From social scientists, I believe what would be meant there would be the relationships. How long you've lived in a community, is there crime? Do you really like where you live? If there's a disaster, would you take that as an opportunity to leave? So I think I would like to direct that first question to Jack, and Chris, also you're welcome to chime in.
That's tricky. I'd actually love to hear from Chris if he's ready.
The whole notion of the power of social infrastructure from the social scientist perspective, from what I've observed, they really believe that if we took care of the social problems and everybody had a more equal ability in their lifestyle, that we would have automatic resilience regardless of the infrastructure. And we know that could be an answer, but that's not this integrated answer. I think the integrated answer is to take a look at the existing environment that we have, and Jack has the models to do that, and to consider the levels of vulnerability, because the folks that are the most vulnerable are also the ones that are the least resilient. And look at the vulnerability and focus our programs and focus the design criteria and how we deal with the existing buildings so that we're really taking care of those vulnerable populations first, the ones that have the most to gain from improving their social infrastructure, and that's a quick recovery as a quick trail to community resilience, if you will.
One thing, Chris, that I would add too is that if the social infrastructure is strong, then I think preparedness becomes strong as well, and that kind of directs people to behave in a different way and in preparation for events that could be very disruptive. So I think there is also a very interesting angle, is how to get the community to be ready for these events. So moving right along, I'm going to take a question from the Q&A, and the first one is from Harvey Bell, and it says, how are the performance engineering assessment methods validated?
That's a great question. It comes up often and rightly so. These models are kind of layered on top of each other, and we're trying to make predictions about extreme events that we don't have kind of detailed empirical data to validate against. I think we are increasingly trying to capture resilience data after disasters and use that to both motivate qualitatively what elements our model should have, but also quantitatively try to validate these. And we've made some limited efforts in that regard. I think the long-term trajectory here in terms of validation is that we're going to validate a lot of model components, right? So the structural, response prediction part, where there's a tremendous expertise through experimental testing and things like that to try to understand what's happening there. As we move to kind of repair costs and repair time for damaged buildings, we can think about collecting empirical data there. The community recovery process is tougher. We can at most collect one data point from a disaster, and each, trying to tease out kind of community specific features versus more general phenomena is hard. So I think it's going to be an ongoing process. It's going to be one we have to pay attention to as this type of work gets more mainstream. I'll also say, though, that I think relative evaluations are much more robust to validation than maybe absolute evaluations. So I tend to not be very interested in kind of the absolute, number of days lost in a particular building to a closure, as much as the questions of, if I'd like to, speed the recovery of commercial office space in San Francisco, can I get a bigger, impact out of trying to have, inspection plans ready, or can I get a bigger impact out of trying to do some targeted retrofits and looking at kind of the drivers of losses or the drivers of impediments to resilience and kind of how to overcome those drivers. I think we can make informed statements about that, even in the absence of kind of the level of validation we might otherwise like to have. But I think it's certainly a important problem and one that's far from resolved in the community.
Chris, the question was how can performance-based engineering assessment methods be validated?
Yeah, the best validation is what happens in each particular event. And it's extremely important that the engineers, if you will, are on the ground every time they have the opportunity. They look at the strong motion records. They consider all the unique characteristics of every earthquake, because every one of them is different. Because it's that intuition that develops from that, as odd as that may sound, but it's that intuition that allows us to look into the simulations and see if they make sense. I know that over the years, as we've looked to develop resilience concepts and the spur work that we did, we kept going back to the 1989 Loma Prieta earthquake, because that was really the only benchmark that we had to try to figure out what made a city resilient. So all I would say is that it takes this on the ground, spending the time, getting the intuition to understand what the consequences are. The other thing I'd like to say is that we need to have a good look at the criteria we use to decide when buildings are safe or not. Jack has this great study that he reported on about cordoning in San Francisco. But the fundamental question is when you look at a building and it's starting to lean, when is it so dangerous that we need to trigger a cordon? And Christchurch had a problem with that because they didn't have, it was a while back, okay? And I won't be at all critical, but the engineers couldn't tell, and to the satisfaction of those that were making the decisions, and they just built a fence around the whole city. And so I think that we really need to pay very close attention to setting our criteria in advance for closure, so that when that moment comes, we don't get unnecessary cordoning going on.
And I do have an observation, and I think this is a really important question, Harvey. Basically, all of our resilience assessments are done through modeling and simulation right now, and even going beyond earthquake engineering to hurricanes and tornadoes and things like that. So the validation is so important to make sure that our models actually make sense. So going on to another question, and this is from a question from the ones that were given in during the registration process. How does risk-based design fit into designing disaster resilient systems, and how is that communicated to the owners? I think the first part of the question to a large extent was answered by Professor Baker's presentation, so maybe we could focus on the second one, is how is risk communicated to the owners?
Yeah, that's Chris, did you want to chime in on that? Go for it.
I'll tell you, my clients and now my community, because I'm involved in this little community where I live, only see black and white. It's either safe or it's not safe. It's either good enough or it's not good enough. And as much as I believe in risk assessment and probability analysis and all the work that Jack and his colleagues have done over the years, and use it as a basis for my understanding and what the decisions I make. That's for us as the design professionals, if you will. We have to take that information and decide and agree amongst ourselves when we have sufficient risk tolerance so that we can make the decisions and tell our owners black and white what's going to happen and what's not going to happen. You might say there's a real problem with liability if I say something's okay and it turns out not to be okay. The reality is as long as we're agreeing on what needs to be done, we agree that what the code should be and we meet the code, and we're exercising a standard of care that's at the state of the practice, our liability is protected.
Yeah, I might add, I completely agree with all that. I might add to that, you know, we do have some kind of interesting developments around kind of building rating systems. This is back to the building level. There's this U.S. Resiliency Council has some kind of ratings, and Arup has developed this READY rating system. And perhaps many of you are familiar with the LEED building ratings for kind of environmental impacts. And rather than kind of going straight to the numerical metrics of energy and consumption or something like that, you can say, oh, I want a gold building or a platinum building or something like that. And that's seeing, you know, it's a hard problem, and it's not going to be solved tomorrow. But I think there is increasingly some, you know, owners that are saying, you know, I understand that a code building maybe doesn't quite get me what I thought I was getting. And it's only going to cost me a couple % more to get this gold building according to some standard. And I'm just going to write into my RFP that I want a gold building according to some rating or something like that. And we may get to a process like that where we have standardization that's not only code mandates, but that extracts, you know, abstracts a little bit away from our numerical analysis that really only the most sophisticated owners are interested in hearing about.
Yeah, and even if, you know, even if they're sophisticated, I think they would have difficulty understanding a statement like this. You know, if a 2% in 50-year earthquake happened, there's a 30% chance your building is going to collapse. I mean, who other than maybe us, our small community, would understand a statement like that? It doesn't convey urgency and doesn't help people prepare any better than what they're doing right now. So moving right along, a question from Professor Ann Jeffers. It used to be that structural engineers focus on the performance of a single building under hazard, but changes in hazard mitigation have shifted the focus to community scale and consideration of many factors, just as Professor Baker talked just a second ago. So for the education of engineers, do we need to teach a new set of skills to our students to broaden their knowledge? How do we bring other disciplines to allow us to look at these city level problems to tackle these increasingly complex issues?
I think that's a good question, and you know, one where to really have an impact, our education needs to kind of follow along with the research. You know, there is a cohort of really, you know, high-end practicing engineers that are developing these things and understand them, but to really deploy at scale, we need kind of educational schemes here. I can speak at Stanford. So 2 years ago, we launched a graduate course in regional seismic risk analysis, where we're bringing in some of these concepts and trying to formalize that and you know, have projects where the students are kind of working through this type of workflow, and they're also working in giving presentations to stakeholders, you know, chief resilience officers at cities and things, to hear kind of the reactions to things and hear the pushback when they get too caught up in the numerical metrics and things like that, or forget about the assumptions they're making. You know, I think some project-based courses where you're partnering with stakeholders, we're increasingly deploying that type of thing. To really understand kind of the context-specific constraints that a community might have, or motivations that they might have, and how that could drive the engineering solutions. So I think those types of things will increasingly be common, just like, you know, maybe a few decades ago, nonlinear structural analysis wasn't widely taught, and now as a part of many students' education, this will be some new tools in our toolbox. We shouldn't solve everything, of course. We shouldn't pretend to be experts in some of the disciplines that we're not you know, solely responsible for, but I think at least having some appreciation of those disciplines and how our work might interface to the policy world and the economic world and social aspects of community resilience is going to be really a great asset for the universities to offer, and for those of you students on the call to be thinking about getting some exposure to those ideas. I think that'll pay dividends in your career moving forward.
I think, Chris, if you would just don't mind for a second, just while we're on that topic, what I think would be really cool if we had something like a capstone project, maybe for a graduate degree, like at the master's level, similar to the undergrad one, where you get people from different disciplines working on these kind of multidisciplinary problems. So Chris, I'm sorry, I know you were gearing up to say something. Please go ahead.
You can tell. I just want to say that for structural engineers, the link is really with the recovery time, the performance of the building. And traditionally, and this goes back a long time, traditionally engineers design to the code. They think that they're going to achieve life safety, and they're very uncomfortable talking about how much damage will occur and how long it's going to take for a building to recover. And there are new tools coming about that are P58 and the USRC rating system that give us an opportunity to talk about recovery. But that's how you get the link from the single building to the community. You can sit with the community, and I've done this, and you can talk about what elements of their community need to recover at what time. But when you turn back around to the structural engineers and say, okay, I need the housing to be recoverable within 3 weeks. I need the hospital to be recoverable within a couple of days. I need the bowling alley, I don't care when it recovers. The engineers have to be able to make that determination one building at a time. And that's a huge challenge and a new place for us to go. Indeed, very much so. Now, there was a question during the registration, and there's a similar question that is in the Q&A, and both of them relate to machine learning and artificial intelligence. And basically the gist of both questions is how can they play a role in community resilience? I know this is kind of beyond the talk that you gave, Professor Baker, but I'm kind of curious about your opinion, and Chris, of course.
Yeah, no, I think it's a good question. We want to think about deploying kind of all of the powerful tools that might be at our disposal. And I think I have kind of two feelings about it. So one is, even though these cities are tremendously complex and smart cities are producing a tremendous amount of data, in some sense we kind of have a small data problem, that these disasters are fortunately infrequent and are many times unique in the characteristics as we move from kind of peril to peril or place to place. And until we have a qualitative understanding of the drivers of resilience, it's very hard to just feed a small data set to a machine learning model and expect that to kind of replace our modeling. So I think our conceptual research and our qualitative understanding of these processes still needs to evolve and is not going to be replaced by machine learning anytime soon. That said, I think there's a lot of role for remote sensing and smart cities to give us information about exposure, or to give us information about human behavior before and after disasters, so to try to understand what are the characteristics of our built environment from imagery and other sources, to understand kind of how are people using infrastructure services by location data, those types of technologies, to understand kind of the inputs to our modeling, I think is tremendously valuable, and we've got a lot of opportunities still in front of us there. But to actually solve the problem from end to end, I don't think it's quite the right application area where just a pure machine learning application is going to solve that problem for us.
Chris, do you have any input, or?
Oh, when you're as old as I am, it's hard to understand machine learning and artificial intelligence to start with. But I appreciate that it's coming. I know that we have areas where we have very, very little information. One of them is just the quality of the inventories of buildings and infrastructure that we have as the basis of our simulations. And if there's some way we can use artificial intelligence to expand the data that we have and learn from that, that would be wonderful. But I have to look forward to seeing that develop.
I agree with you. I think if the very first question that was asked regarding validation, if we have validated simulation models at the regional level, and those are multidisciplinary, they might include social science, health, transportation engineering, structural engineering. If those models exist, and I think people are going in that direction. And once you have these validated, what should I call them, like urban scale simulations, I think you could use some of these machine learning models there to kind of run many simulations, teach the model, and when an actual event happens, then you might be in a better position to optimize your response. I think machine learning is very specific. And if you, like you said, Jack, if you have a good training set, you're going to get a good result for that. So that's the issue right now, is that I don't think we have the data for it, but I think we are going in that direction. It's going to be really interesting to see how that goes. So I'm going to, I don't know, I'll take a shot at this question. I don't know, Jack, if you have an answer to it or not, but it's a question from Professor Jeremy Bricker saying, this is great that you're moving towards a probabilistic risk framework. What source is the most reliable for the depth, damage functions, and fragility functions? So I know that's more on the water side of things. Are you
Yeah,
comfortable
that's
answering the question?
I think, yeah, depth damage is a one we struggle or continue to struggle with. I mean, there's a variety of sources we use. Kind of U.S. Army Corps of Engineers has us depth damage functions frequently. You can go to somewhere else and be convinced that those are terribly off. You know, and so rather than give you a concrete answer there, I'm going to shift the question slightly and say, you know, I think this points to like there is no substitute for kind of fundamental engineering knowledge in many of these components of the analysis, and I don't think kind of moving to these broader questions at all reduces the need to understand component pieces of the puzzle. And I think depth damage functions is one of those examples where further kind of discipline specific research is needed and data gathering is needed. That work is of course ongoing, and I think it'll be valuable because it doesn't mean that we've solved these problems or that they don't matter anymore, just because we're shifting the questions we're asking using them.
Chris, would you care to comment on that, or we can move on if you don't want to?
That's great. We can move on.
Okay, all right. So another question from Professor Fotios Iwano, and given the time, this might be the last one. It says, who do you see as the decision makers? And like, are they state, county, city, owner, designer? And how do these decisions permeate down to the actual design and the legal responsibility of professional engineers?
Chris, I think you'd be great on that.
Who are the decision makers? Well, it depends. You know, one of the best tools that we have to build infrastructure resilience is in the design standards and the building codes, and that rests right with the engineers. And there's a lot of conversation that goes on amongst engineers about what's appropriate, not appropriate, how we achieve functional recovery levels, and all that. From that standpoint, it really rests on the shoulder of the engineers to continue to drive that forward and provide those tools. When you get up to the owner's level, what they're really talking about is how they're going to invest their money. And they make the decisions about whether they're going to build buildings better or not. And that's really going to be based on what the engineers tell them they're going to get back from it. When you get to the state and national level, we're really talking more about mitigation programs and what's going to fund the mitigation programs and how those are going to happen. And then those come down to trying to balance the opportunities we have in disaster mitigation, along with all the opportunities that are out there to spend money on at the federal level. And that gets extremely difficult. And honestly, it really happens very, very rarely. San Francisco's mitigation program for soft story buildings really occurred because of the 1989 earthquake and the loss of those buildings. Without that kind of a trigger, these programs don't really go off, don't really come forward. So in that regard, I just finished by saying that the building code standards and the design standards we have and the ability to deliver recovery times and help owners make proper decisions one building at a time is key.
So Chris, actually following up on just what you said, and there's a question from Professor Roskorotis, which is saying, and it was directed to Jack, but I think I would like to direct it to you first, and this is the last question we're going to take. It says, could your approach be used to help communities develop reward measures? So rather than thinking of the owners thinking, oh, I just want to make money, could there be a reward measure for retrofit that would help bridge the gap between the time horizons of elected officials versus long-term infrastructure planning, which is another big issue, of course?
You know, the reward programs really work in terms of incentives that go to building owners and infrastructure owners. And I think that's where the focus is that those, whether it's in terms of tax credits or grants or various ways that are maybe modifications to the building standards, those kind of reward programs that get right to what at the heart of where a building is and a building owner is, I think could be useful.
Thank you. Jack, do you have any final comments?
Yeah, I think that makes a lot of sense. Maybe I'll add one thought from like the research community or from the modeling perspective is that a lot of times in these situations, I imagine kind of a risk trajectory over time that we have kind of this, under a status quo, we have this growing risk over time. And the problem is these consequences are, yeah, maybe far in the future, an elected official might think they could dodge it or doesn't want to spend money now. And so we really need to quantify that trajectory out into the future. And we need to quantify how it would change under some alternate reality where we're taking action. And until, it's going to be too late by the time we observe these consequences. And so to have credible models to forecast out, this is what we're facing, and this is what we could face if we take action now. I think that's not the only piece of this puzzle. That's not going to be sufficient to solve the problem, but I think it'll be a very valuable bit of ammunition in our tool belt to try to make the case that action needs to be taken far in advance of when these disasters might actually face us.
Thank you very much. With this last question, I think we should shut down this session and move on to the student session. I'd like to thank you, Chris, for your work today as a panelist and the thoughts that you gave, and Jack for your thoughts as well, and for the really nice and very succinct presentation that you gave as well.
Excellent.
So certainly this is a topic that affects all of us. Resilience is something that is, it's a worldwide issue. And I think there's increasingly more people that are working in this area. And I think that some of the questions that were posed today are very, very pertinent to that. So I'd like to thank everyone for attending. And I would like to ask you to please visit umservice-to-society.org, where we talk about our strategic vision as a Department of Civil Environmental Engineering. As Professor Lynch mentioned early on today, this is not only we don't see this as only helpful to us as a department, but hopefully for our profession of civil environmental engineering. And we'd like to ask you to also provide your thoughts by going to the chat, and there's a link there for you to give us some feedback. So thank you all again. We're going to close down the session. Thanks for your attendance.